everyone. Um, it's my honor to be here to give you a talk about our recent work, MarsonRay, accelerating large-scale tensor and data frame workloads. I'm Chris Chin. Now let me introduce myself. I'm a senior software engineer at Alibaba Cloud. I'm now focusing on Mars as core developer and architect. Before that, I developed a framework named PyODPS, which supports pandas-like syntax that you can write the data frame things, and under the hood, the data frame operations will be translated into SQL to run on big data platforms and the databases, including the PostgreSQL and MySQL. So let's talk about Mars. So I need to talk about the workloads that we have inside the company. First, we'll talk about the tensor workloads. The first important workload is the knowledge graph. We know that knowledge graph can be encoded as the sparse tensor, and the users often apply quite large tensor operations like matrix multiplication and the matrix decomposition and so forth. So it's the knowledge graph is always relatively large. So the speed is very crucial for this kind of workload. Another workload is the vector search. It's widely used in like entity search, like picture search or recommendation system. Any entity can be described as a vector. So we have, for example, take the recommendation system as an example. We can describe a user as a vector, and we can describe the item as vector. So if we want to recommend some items to the user, we can just find the vectors that is has the distances that are the smallest ones. We can use the cosine distance or Euclidean distances. That means if the distance between two vectors is small, means that they are very similar. So we can recommend that. But consider the situation that the vectors could be very, very large, maybe billions of vectors. And if you use the brute force algorithm, you know, it's quite a huge computation, because you have to compute every two pairs vectors, so it's extremely heavy for the computation. Another workload is the data processing and post-processing for machine learning. We know now the deep learning is super popular now, but the pre-processing is inevitable. The pre-processing can be the normalization, splitting the try and test data, and so forth. And after the machine learning, you have to do some matrix or do some visualization. So it's very also important. For data frame workloads, we have some kind of data exploration. Here I'm talking about some auto data exploration. Given a large data frame, the user wants to know if there is any missing data in for the columns, or the distributions of the columns in the data frame and so forth. So the user always want to do some automatic data exploration, and the user always view some slice of the data. So they must make sure that even the data is large, the slice of the data frame can be fetched very, very quickly, so that they can just do some check some about the data. Another one is very popular for the data cleaning. You need to remove some corrupted data or fill some missing value and so forth. The users also analyze the data. They do some aggregations, do some group by, and so forth. The last one is visualization. The data will use Matplotlib, Seaborn, or do some interactive visualization like Broadly or Bokeh or so forth. So in the past, the user are very familiar with the traditional data science tools. The data science tools can work perfectly on their laptop, like NumPy. The user can manipulate the ND array, and SciPy is another one. User can use SciPy for some scientific computing, and Pandas is also important. Pandas is a the user can use pandas to analyze the data. And the last one is scikit-learn. Scikit-learn is a super popular machine learning platform that user can do some traditional machine learning and the pre-processing, post-processing, and so forth. So the traditional data science tools is very popular. Uh, they are used by millions of people, and they can fit for not so large data. The data has to be fit into the memory, and they are super easy to run on a laptop. Like you can just install them via pip or conda. Pip install NumPy. So their performance is okay because the underlying code is C or Python or Fortran. So the performance is all right. But nowadays, the data is getting larger and larger. And for a single data frame, there can be billions of records. And the user don't want to learn something that they are not familiar. We think that the user just need the familiar APIs so that they can make some smooth transition. So we think the familiar API is very important. Um, and we have a large cluster up to thousands of workers and for a single cluster. And maybe I will have a lot of clusters. And for a single task, it can use up to 12,000 cores. And we must make sure that the user can set up their environment very easily, just like the traditional data science tools. So we developed Mars. Mars has a familiar API for NumPy and SciPy. You can use Mars Tensor. For pandas, you can use Mars DataFrame. For scikit-learn, you can use MarsonRay. Now we can see it from a high level view. I've mentioned the fundamental components. The Mars tensor is actually the distributed NumPy, and we support various data format for tensor like HDF or ZAR or so forth. And Mars data frame is actually the distributed pandas. And we support also support various data formats as well, like Pocket, CSV, or the databases like MySQL, PostgreSQL, or even ClickHouse. The last one is Mars Remote. It allows users to distribute their bunch of Python functions to run in the cluster. It's a little bit like the array tasks. And above that is the machine learning and integrated libraries. MarsLearn is actually distributed scikit-learn, and we have integrated quite a bunch of popular Python libraries for machine learning like TensorFlow, PyTorch, XGBoost, like GPM, and so forth. And beneath the APIs things, we can take a look at the internal stuff. We support various platforms. The Ray is the most important, and Kubernetes and Yarn are supported as well. And we actually make an abstraction called Oscar. It's a lightweight actor framework, or Mars data or Mars. The runtime is built on the Oscar. So the Oscar provides a actor API, and leveraging the Rails facilities, we leverage the Rails facilities as many as possible. So it's quite easy to implement the Oscar based on the Ray actor API. And we use the ray serialization, the RPC, the object store, which enables object spilling. Yeah, so the OSCAR could be very easy to be implemented on based on the ray. But for the Kubernetes and how to be on, we have to on our own. The communication is via Unix socket if they are on the same machine, or the socket if they are across some machines. And we have our own serialization based on the Pico5 protocol. Based on the Mars actors, we we separated the Mars the runtime into quite a few different services like the session, meta, and the storage, so that we can separate them into different modules, and each service has an API. And for a service, if they want to call another service, they have to use the API, so that we can decouple some modules to make the implementation of Mars more clear. Now, let's look at the API. The Mars tensor is quite similar to the NumPy and the SciPy. Take the black squares as the example. It's very popular in the financial area. So how about Mars tensor? What you need to do is just replace the import from the import numpy SMP to the import mars.tensor SMT. So that's the SciPy API from mars.tensor.spatial import ERF. The function is just identical. Yeah, and another difference is that you have to call the mars.execute to trigger the execution. That means Mars is by default a lazy evaluation. So you have to execute it if you want to get the result. Mars DataFrame is pretty similar. What you need to is from the import pandas as PD to import mars.dataframe. And the plot has done the execute for you because actually if you want to trigger the execution, you have to call the execute by yourself, but plot has done it for you, so you don't have to worry about that. MarsLearn is pretty similar, and you can import from the scikit-learn.neighbors to mars.learn.neighbors, and the other process almost the same. And also the kneighbors has triggered the execution inside it, and so that's the other neuron APIs, including the feed, predict, kneighbors, and so forth. So for now, the Mars Tensor DataFrame Learn has implemented the subset APIs of NumPy, pandas, and scikit-learn. But in the long term, we hope that we can implement a superset. Superset is actually our goal. The reasons are the first, some ops are born for distributed, but they are not actually needed for if you are running some code on your laptop. For example, the map trunk, the Cartesian trunk, and the map produce or something. Let's take the Cartesian trunk as an example. Sometimes you want to for a record in the df1, you have to make some computation over the entire data set of df2. So for pandas, you have maybe you can just apply a function to the df1, and in the function you can just iterate over the df2, or it's not a big deal. But consider the situation that the df1 and the df2 for a distributed setting have a bunch of workers. The data may be allocated to different workers, so you cannot just for loop or make some for loop or the similar stuff. So what you can do for Mars, you just need to write a function. Maybe in this example is completed a process. What you need to do is just to process the one chunk of the df1 and one chunk of df2. You can just put the same logic into the function, and the Mars will make sure that each chunk of df2 and each chunk of df1 and df2 will be called. So it's very crucial for the distributed systems if you are using such APIs. And the second reason is that some apps may run differently according to different situations, maybe the numbers of workers or the data size or the data pattern. So there are maybe various algorithms under the hood for the same LP. For example, we take the group by and the AGG as an example. If the group keys are relatively small, we can apply the tree-based algorithms. We can do the group by AGG to each trunk, and we concat a few trunks, and we apply the group by AGG and then concat, so it will become a tree. It's very efficient when the group keys are very small. But the downside is that if I have many group keys, the final data, if you still apply the tree-based aggregation, the final data will be super large. They can be too large to fit into the memory. So we may use the shuffle-based algorithm. So first, that you still apply the group IgG to each trunk, and you will just shuffle the data to make sure that the same key will be shuffled to the same worker, and they can apply the group IgG until then. So the algorithm may be different according to the different situations. And the last reason is that there are some different algorithms for machine learning. Like the scikit-learn provides for the nearest neighbors. The scikit-learn provides different algorithms like the brute force that they will compute each pair of vectors for the x and y. And there are other algorithms like KD tree or ball tree, but the algorithm is not very, it does not work well for the distributed setting. So we have other algorithms beyond the scikit-learns. So here we have the algorithm Proxima. Proxima is a library that are highly optimized for nearest neighbors. And we can just compute the nearest neighbors to a large data set. Like, for example, we have the 400 million vectors to search, and the 400 million vectors to index, and the 400 million vectors to search. So if you apply the brute force algorithm, it's super huge computation because you have to do the multiplication of the size. Actually, we use the approximate algorithm, and it takes about 3.5 hours, including the reading and writing the data frame time. So, and even for the brute force algorithm, it's 4 to 5 times faster than the scikit-learn based implementation. If you set the algorithm to brute, in each trunk, Mars will just apply, just delegate the computation to the scikit-learn. And if you specify the Proxima as the algorithm, is about 4 to 5 times faster. So that's why we want to build a superset instead of subset. And we have mentioned that Mars is kind of a lazy evaluation. If you do not trigger the execute, if you just display A, you will be told that it's a tensor, what the OP is and the shape and so forth. Until you call the execute, you cannot get the result. But Mars just offer eager mode as well. You can just specify the eager mode to true, and then each time it display a tensor data from and so forth, it would just tell you the result. But for a lazy evaluation, it has better performance because we can just fuse the intermediate nodes that the user does not care about, and the graph size will be very small. And we can do many optimizations, just like fuse or something to just to eliminate the intermediate result. And we can schedule it more efficiently because we can just um, um, make sure that the intermediate uh, node will not occupy too much memory. It can save more memory usage. On the other hand, the eager mode has worse performance because each Mars object has to generate data. That the data has to be stored in the cluster. So unless the object is GC collected on the client side, the Mars will delete the data in the cluster as well. And it's hard to optimize because you don't have pretty much intermediate results, so you can not do many optimization. So is there any better solution? The answer is yes, we are developing a defer mode. The defer mode does not require the execute as well, but we will try to do the lazy evaluation as much as possible. It's still under, we will still try to implement this functionality, so stay tuned for the functionality. And now I will show how Mars and Tensor DataFrame scales the workloads. Let's take a example, code as an example. We have a bunch of objects showed. The first is the operand, and we have tileable data, which is the DataFrame data or the tensor data or source data and so forth. And we have the tileable, that is the DataFrame or tensor or so forth. So we call the ones. It will just create an operand called the ones and has tensor data on the client. Please remember there's no actual computation so far. We just created tensor A that it has just a data property that points to the tensor data, and the user set some value in the tensor. So we'll create another operand called the index set value, and it creates another tensor data, and then we just point the data of tensor A to the new tensor data. So we can just discover that the tensor data is immutable. The immutable is very important for the distributed setting. We don't have to care much about the consistency or so forth. So now we'll create another data frame. It's pretty the same. And the last we call the sum. We have a series data. So when the user trigger the execute, the graph will be uploaded to the supervisor. We'll have a bunch of characters in the cluster, like a supervisor and the worker. And after the graph submitted, the tileable graph will be optimized into another tileable graph. Tileable graph, the optimization could be the column pruning or so forth. And we'll do a really important operation called the tile. Tile is very important in Mars. Yeah, we can take an operand as an example. Basically, for an operand, we have to implement two functions. Like the first is the tile. It will tell the supervisor how to tile able into trunks. And the second function is the execute. We'll talk about it later. Yeah, when the tile graph is able to tile, we'll just just use the topological order to iterate over the graph and tile each operand. Here we have one's tensor, whose shape is 10 by 10, and the trunk size is 5. So two trunks on each dimension. So the final chunks is 4. And then the set value only affects one chunk, so we just apply one chunk to one operand to one of the chunks. Then create the data frame from tensor. And finally, the sum will just do the tree aggregation for the users. Now the trunk graph is ready, and there will be optimized. The fusion or so forth will be applied to get the final trunk graph. Maybe the operands in the line will be fused into one fused operand, and so forth. So we have the final trunk graph. We will just schedule the trunk graph to all the workers for the distributed running. Each operand will be a subtask. The subtask will have the subset of the entire trunk graph, and the subset will be scheduled to a worker according to a pretty complicated scheduling rules. But to simplify it, there are two crucial rules. The first is the depth first. We need to schedule the nodes that has a deeper depth that it can be pretty much closer to the final result, so we can just free the intermediate data as soon as possible. The second rule is the locality aware. We must make sure the data has to the operand has to be run on the node that owns the data. So because the data transfer between two nodes are too time consuming, so we need to schedule the calculation pretty much closer to the data. So the subset is scheduled to the worker, and when it's finished, we can tell each operand is just executed by the execute function. And for the function, there are two arguments. The first is the data for the inputs, and so does the operand. When a subtask is finished, the successor will be scheduled as well. So all the works will run over the subtasks until they are finished. So we'll give a tour of MarsonRay job. First, we start a new cluster, and inside it, we will create a placement group according to the numbers of workers and the CPUs. And we will create Mars supervisors and workers. Each of them consists of several Mars actor pools. It's the Oscar part. Each Mars actor worker actor pool will be wrapped in one Ray actor. And we will create more services like the meta task. And one service will create a bunch of Mars actors. Each actor will be allocated to one Mars actor pool. And then we'll create a new session and set it as default. We'll connect to the cluster we have created. And at last, we'll call the execute. The Mars task will be submitted to the supervisor. And when the computation is finished, the data will be fetched to the client to display. Now, just take a look at the cluster start part. Due to the reason that Ray simplifies distributed applications, it's pretty easy. Here we have two workers to start, and each work has two CPUs. Inside it, the placement group will be created. The bundles tells that the service supervisor uses one CPU, and the first worker uses two CPU, and second worker two CPU. So that's the memory. And the Mars actor pools will be created. The first for the supervisor, and the others for the workers. Each of them is actually one Ray actor. And the Mars actor will be created inside one actor pool by a task or a service like the task service. And so does the subtask service. The subtask will create a bunch of actors on different actor pools. the storage service will also create a few actors. It's Mars actors to clarify. And the storage service will just use the object store, the array object store that enables object spilling. So when the data cannot be fit into the memory, the spilling will try to spill the data that not used maybe not used recently into the disk. And the data transfer can also be handled by the array itself. We don't have to care much about the data transfer. And so that's the array actor core, the Mars actor core. The Mars actor core can just become a array RPC core. So we need a few more works in the near future. The first is we need to try to leverage the ability of array to make a faster failover. So when one worker died for a reason, maybe the out of memory or something, we can just fail over quite quickly by leveraging the ability of array. And auto scaling is super important. The users does not need to don't need to care about how many workers they need. We can just auto scale the clusters according to the data set or something. We need an algorithm to decide how many workers we need. And we can just leverage the locality-aware scheduling of array, which is pretty recently implemented feature, and we can generate a subtask that faces more ops that can leverage this kind of scheduling feature. And the Mars task can, in the array cluster, there can be other applications, not just Mars. We hope that we can interact with to maybe reduce the data transfer cost or something in the future. So let's take a look at the demo here. Now we start a cluster. Yeah, we just wrap the new cluster function. And the user has to know about the worker noun, yeah, to decide how many workers. Now we start a worker, and it will print the array dashboard, and we can just click the dashboard. Yeah, we can see now the actors is 0, and we can refresh. We will see a bunch of array actors are created. Each actor is actually a Mars actor pool. Yeah, now the cluster is ready. Now we can just do some Mars computation. We create a Mars tensor from numpy and array, and we create a Mars tensor that is relatively large. And we can just do some DataFrame computation. And okay, it's pretty much like the pandas itself. Okay, that's all the demo I want to show. So conclusion, the MarsonRay is still under quick development. We're doing a lot of work, like I have mentioned. And with the power that Ray enables, the MarsonRay could be not just two separate projects. They can be much better. The MarsonRay documents here, and you can track the progress of MarsonRay on Mars project. And you can try out Mars as well. You can just pip install py Mars to install Mars. It's actually pretty easy. And don't forget to start our project on the GitHub. Our address link is here, and the document. Thank you. That's all my talk. Thank you for your time for listening. Thank you.